All right, so last time we talked about the definition of a logarithm, and you got a lot of practice with converting logarithmic equations to exponential equations and vice versa. Um, so today we're going to expand on that and talk about the properties of logarithms. Okay, so remember the definition of a logarithm. You've got that, and we can express a logarithm log base b of y equals x as b to the x equals y. Okay, so the log base 2 of 32 equals x is the same as 2 to the x equals 32. So the logarithm is asking, what's the exponent on 2 that gives you 32? So remember, the log is the exponent. All right, so by this definition, there are some properties that just follow directly from the definition. All right, so one of those properties is that the log base b of b is equal to 1. All right, and why is that? All we have to do is rewrite that logarithm as an exponent, and we can see why it's true, right? Because this is saying that the log base b, right? So the base is b. The exponent is 1 because the log of b is 1, and the result is b. And that seems pretty straightforward. B to the first power is b, so that makes sense. The same way with this next one. The log base b of 1 equals 0, because if we rewrite this as in exponential form, b to the 0 is equal to 1, which is true. Okay, so this third one, again, we just can write it in exponential form. B to the x equals b to the x, and that seems obviously true, right? All right, so one more property here that follows directly from the definition of a logarithm is that b to the log base b of x is equal to x. This one is not quite as straightforward as far as just rewriting it as a logarithm, but think about what the log base b of x is. The log base b of x is the exponent on b that gives you x. So if we raise b to that exponent, we get x, right? Just by definition. The log base b of x is the exponent on b that results in x. So it makes sense. All right, so those are pretty straightforward. So I'm going to pause the video here and let you try this first example on your own, because I think you'll get it. And in the meantime, I will write out the answers, and you can check them when you come back. All right, so here are the answers to the first example. And so check your answers. If you didn't get these answers and you're not sure why these answers are correct, then just ask me in class, okay? Or ask me in my office hours, email me, whatever you need to do. But let's go on to the next property of logarithms. All right, so next property I'm going to talk about is the equality property of logarithms. All right, now the equality property of logarithms just follows directly from the equality property of exponents. So let's remind ourselves what the equality property of exponents says. It says that if two powers of the same base are equal, all right, so let me see if I write that. If two powers of the same base are equal, then their exponents are equal. Okay? All right, so given that, let's take a look at what this says. The equality property of logarithms says that if you have two logarithms that are equal, then the arguments are equal. Okay, so just remember what the logarithm is. Log is the exponent. Okay, and we can always express a number as a base to some power. Okay, so we can actually express m as b to the x. We can express n as b to the y. So basically we have m and n are just, we could write them as two powers of the same base, which means that their exponents are equal. And remember that the log is the exponent. Okay? So there's also down here a little bit more of an algebraic argument for this property. You can take a look at that if my explanation didn't make sense. But let's take a look at how we can use this property. This property is actually one of the more powerful properties, which we'll see more later. It may seem kind of trivial right now, which a lot of things in math seem trivial at first, and then you realize the power of that of that trivial idea. Okay, I want to also point out that a warning here, that when you solve logarithmic equations, you have to be careful because you can get extraneous solutions. All right, we can't take the logarithm of a 0 or a negative number, okay, like we saw last time. And so if your solution results in a number that causes the original equation to have a logarithm of a negative or a 0, then that solution is not valid. So, but we'll get to that. I'm going to show you an example of that in a moment. All right, so we're going to use the equality property of logarithms to solve these equations. So we have the natural log of x plus 4 is equal to the natural log of 3x minus 8. So if the logs are equal, then the arguments are equal. So all we have to do is set these arguments equal to each other. 3x minus 8. Okay? And so now that's just an algebraic equation that we can solve. So I guess what I'll do is I'll subtract x from both sides. So I'll get 2x over here. I can also add 8 to both sides. So I can get 12 over here on the left, which gives me, when I divide both sides by 2, x is equal to 6. Okay. So with a logarithmic equation, we have to make sure that we check our solution. And so all you need to do is put this solution back up into the original equation and just make sure you're not taking the logarithm of any negatives or zeros. So if we put 6 back up into the original equation, we get 6 plus 4 is 10. Okay, we can take the logarithm, the natural log of 10. Same over here, we get 18 minus 8, again, which is 10. We can take the natural logarithm of 10. So that checks out. So that's our solution. All right, I'm going to leave B and D for you to do on your own. I'm going to go down here, though, to C, because this is one where we have a problem. Okay, so we could just do the same thing. We have a natural log of x squared plus 4x equals the natural log of x minus 2. So that just means that x squared plus 4x equals x minus 2, right? The arguments have to be equal. So this is basically a quadratic, but we need to put it into standard form in order to solve it. So let's rearrange it a bit. We can subtract x from both sides, which gives us plus 3x, and we can add 2 to both sides, and that's equal to 0. So now it's in standard form, and we can factor it. So we get x plus 1 times x plus 2 equals 0. Okay. So to solve this, we're going to use the zero product property, which says that if the product of two things is equal to 0, then one of the two factors has to be equal to 0. So either x plus 1 is equal to 0 or x plus 2 is equal to 0. If x plus 1 is equal to 0, then x is equal to minus 1. And if x plus 2 is equal to 0, we get x is equal to minus 2. Okay, so we've solved for x, but again, this is a logarithm, so we have to check. All right, if I let's just take negative 1 first of all, put it back up into this, the original equation, I get 1 minus 4, the natural log of 1 minus 4, which is the natural log of negative 3. Can't do it. All right, so that's not a solution. That cannot be a solution. Let's take -2. That gives us 4 minus 8. Natural log of 4 minus 8 is a natural log of -4, which again is not going to work. So that is not a solution. So even though we went through all this work to solve this logarithmic equation, neither of those solutions work. So for this logarithmic equation, there is no solution. Okay? All right. So I'm going to pause the video here. I'm going to have you take a look at B and D. And then when you come back, you can check your answers. All right. So here is the solution to these two logarithmic equations. In the first one, I got plus and minus 3. Okay, both of those work. If I put in plus 3, I get 9 minus 1. That's 8, so log of 8 is equal to 8. Oh, that works. Okay. Same way if I put in -3. That also works, because -3 squared is positive 9. 9 minus 1 is 8. Okay, so those both work. Okay, so check. We verified that those both work. Let's take a look at the second equation. I got x equal 1, which is the correct solution to this algebraic equation, but I need to put it back into the logarithmic equation to make sure it works. So 2 times 1 minus 4. Okay, that's a -2. We cannot take the log of -2. Okay, same way on this side too. Doesn't really matter. You can only have to really check one side, but that gives us a log of -2, so that is not a solution. So this equation has no solution. Okay, so the moral is you need to check your solutions when you're dealing with logarithmic equations. All right, so let's go on to the next property, the product property of exponents. So again, remember, the log is the exponent. So this is saying the exponent on this product, m times n, is equal to the sum of the exponents of m and the exponent of n. So you can see it follows directly from the product of powers property for exponents. Okay, the product of powers property for exponents basically says that the exponent of the product is the sum of the exponents. And if you express m and n as powers of b, the base, then this is saying that the exponent of the product is the sum of the exponents. So it basically is the product of powers property for exponents. Okay. Again, I have more of an algebraic proof down here of that, but I want to make sure you understand. If you understand this stuff, it just makes sense, and then it's a lot easier. You know, I'm not one to memorize stuff. You'll find, and so I don't have to remember it because it makes sense. So, all right, let's just do a couple of problems here. All right, so we have the natural log of a sum. All right, we can use the product property to combine these into one logarithmic expression, right? We can the sum of these logarithms is equal to the logarithm of the product. Okay, so e squared times e to the 7th. Okay, so we've written it as a single logarithm, which is what we're asked to do here. So, but we can actually take this further, right? I can see that that's the natural log of e to the 9th, right? Just by adding those exponents, which is what you do with exponents. And the natural log of e to the 9th is just 9. Okay, so I've taken it a little farther than I needed to. But also, I can also just go back up to this this original expression here, and I know that the the natural log of e squared is 2, and I know that the natural log of e to the 7th is 7. So you can see I get the same answer either way. Okay, so it kind of gives you an idea of why the product property works. All right, here's another one. I'm just going to express it as a single logarithm. So we have the log of 0.1. So we have the sum of logs, so we're going to express it as a product. Okay, so it's the log of the product. 1,000. Now it's the log of the whole thing, so I'm going to put some brackets around here, just so you know it's the log of that whole thing. Okay, now again, that's all we really needed to do with this problem, but I can actually take it farther. That's equal to the log of 0.1 times 1,000 is 100, so it's the log of 100. And the log of 100 is just 2, right? Because 10 to the second power is 100. Okay, again, just like before, I can actually just use this, I can just solve these logarithms up here. I know that the logarithm of 1/10 is -1, and the logarithm of 1,000 is 3. So either way, I get 2. All right. So let's take a look at this one. All right, we're just going to express it as a single logarithm. So we have the natural log of x times 2x plus 3. Okay, and it's the log of the whole thing, so it's good to put brackets around it. Now, there really isn't anything else we can do with this. I mean, we can multiply, we can use this distributive property and multiply the x through and get the natural log of 2x squared plus 3x if we want to. But we don't really need to do that because all we're asked to do is to express this as a single logarithm. Okay, last one, log of 2 plus the log of 5. Okay, I can take that sum of logarithms and express it as the log of a product. So I get the log of 2 times 5, which is the log of 10. Okay, we know the log of 10 is just 1, so I can just express that as 1. Okay, so all right, let's go on to the next property here. Scroll down. All right, the quotient property. So the quotient property of logarithms follows directly from the quotient of powers property for exponents. Okay, so the quotient of powers property for exponents just says that the exponent of the quotient is the difference of the exponents. And because the log is the exponent, okay, and we can express any number as a power of a base, okay, I can rewrite any number as b to the x, as some b to some power, okay. So you can see that here we have the quotient of powers, all right, so the exponent of the quotient is equal to the difference of the exponents. Okay, it's really saying the same thing. All right, so again, I have a little bit of an algebraic proof here that you can take a look at, but let's go ahead and apply this. Okay, that's fine. And let's show how it works. Okay, so these first ones are you know, kind of the analog of the problems we saw just previously with the product power, the product property. So we can write this as a single logarithm if we just write natural log of e to the 5th over e squared. Okay, that's all I really have to do, but I can actually simplify that more. Natural log of e to the 3rd, right? Because e to the 5th divided by e squared is e to the 3rd. And the natural log of e to the 3rd is 3. All right. Yep. And I can, just like before, I could actually just do this without having to express it as a quotient. I know that e to the 5th is 5, and I know e squared is 2. So either way, I get 3. So that's good. It works. All right, let's express this one as a single logarithm. Again, we have, oops, this is the log base 10, so I'm just going to write log And we're going to express this as a quotient. We have a difference of logarithms, so we can express it as a quotient. And so it's the log of 1,000 over 10. But I can keep going if I want. That's just the log of 100. And that's equal to 2. But if you look at this, the log of 1,000 is 3, right? Because 10 to the third power is 1,000. Log of 10 is just 1, right? So either way, I get 2. So that's nice. All right, let's write this as a single logarithm. Okay, we have the natural log of 5x minus 1 minus the natural log of x minus 3. So I can express that as a quotient. That's the natural log of 5x minus 1 over x minus 3. Okay, I'm done there. There's not really much else I can do with that. All right, one more. Let's express this as a single logarithm. The log of 300 minus the log of 3 can be expressed as the log of 300 over 3. Okay, which is, again, that's all I really needed to do. But that's the log of 100, because the 300 minus 3, or 300 divided by 3 is 100, so that's 2. Now, if we look back up at this original expression, can we get 2 without expressing this as a quotient? So one thing you could do is actually write 300 as 3 times 100. So we can actually write this as the log of 3 plus the log of 100, right? I'm using the product property now, and I'm expressing 300 as 3 times 100, so that's the log of 3 plus the log of 100, and then I still have to subtract the log of 3, okay? So you can see, okay, now we have the log of 3 minus the log of 3, those cancel, okay? And we can see that we're just left with the log of 100, which we know is 2. So there you go. We can actually do it either way without expressing it as a quotient. All right. Next property is the power property of exponents. So, oops. All right. The product property. Now, again, this follows directly from the power of a power property for exponents. Okay. So, again, the log is the exponent. So we have, and we can express any number as a power of the base. So if you think of m as the power of a base, then the power of that power raised to the p power is going to be the product of the exponents. Okay, the exponent of m raised to the p power is the product of p times whatever the exponent takes to get m by raising b to a power. Okay, b to an exponent. Okay, so again, I have a little bit of a algebraic proof here, but this is actually a very powerful property for solving exponential equations. So let's see how this works. Now these first two are pretty straightforward. Okay, what I'm going to do is just use the power property to bring the x out in front. So the log of 2 to the x is x times the log of 2. Okay, equals 3. So I'm just using the power property to bring that exponent out in front. Okay, now this problem says to solve for x in terms of log 2 and log 3. Okay, so I don't have to actually solve it for an actual number, a decimal approximation. So all I need to do, log of 2 is a number. I could put that into my calculator if I wanted to, and get a decimal approximation for the log of 2. But all I'm going to do is just divide both sides by the log of 2. So x is equal to 3 over the log of 2. Right? Okay. So that's it. That's all I need to do because I'm expressing x in terms of the log of 2. Okay. All right. So let's take a look at this next one. Again, I'm just going to use the properties of logarithm to bring this exponent out front. That's the beauty of the power property, is it allows you to bring the exponent out of out of that exponent position. Okay, so we have x minus 4 times the log of 3. All right, I know that's true by that property of by the power property of logarithms. Okay, oops, log of 2. So now I want to solve for x. So I'm going to say x minus 4 is equal to the log of 2 over the log of 3, just dividing both sides by the log of 3. And now I can add 4 to both sides. So x is equal to the log of 2 over the log of 3 plus 4. All right. Now, notice these next two do not have logarithms. So now we are going to use the equality property of logarithms to solve these. The equality property of logarithms says that if you have two equal things, all right, these are two equal things, then the log of those two equal things is also equal. So by the equality property of logarithms, we know that the log of 3 times 2 to the x equals the log of 10. Okay. All right. Now that allows us to get the x out of the exponent position. All right. So I'm going to use the product property over here. I'm going to say this is the log of 3 plus the log of 2 to the x equals, and I know the log of 10 is just 1. Now I can, I'm just going to subtract, well, actually, I'm going to take this logarithm right here, and I'm going to write it as x times the log of 2, just bringing that exponent out front. And then I'm going to subtract the log of 3 for both sides, so 1 minus the log of 3. Okay. Now I can solve for x. So x is equal to 1 minus the log of 3 over the log of 2. Okay. All right, one more here. Again, I'm going to use the equality property of logarithms to figure this out. All right, and that allows me to take the log of both sides. So I'm going to do the log of 3 to the x plus 1 equals the log of 20. That allows me to take the x plus 1, bring it out front, and I'm left with the log of 3. Now the log of 20 is actually the log of 2 times 10. Now, and I'm doing that because the problem is asking me to express x in terms of log of 2 and log of 3, not log of 20. So what I'm going to do is I'm going to express 20 as 2 times 10, so that gives me the log of 20 is the log of 2 plus the log of 10. Okay, now I know what the log of 10 is, and now I have it expressed in terms of the log of 2. All right, now I want to solve for x, so I'm going to say x plus 1 is equal to the log of 2. Log of 10 is just 1. And I'm going to divide both sides by the log of 3. Okay. And now I'm just going to subtract 1 from both sides. So x is equal to the log of 2 plus 1 over the log of 3. All right. And I'm going to subtract 1, minus 1. Okay. All of that I can put into a calculator and get a decimal approximation for x. I'm not going to do it because that's not what the problem is asking for. Alrighty. What's next here? All right, I've got one more problem that I wanted to go through. And then I'm going to give you some practice problems to work on. So I'm just bringing up this problem just because you're going to see some problems in the homework, maybe some problems on a quiz, problems on a test that look like this. Okay, so we're going to use the property of logarithms to solve for t in terms of a, b, and c. All right, so I have a product, and I have a power, I have also a quotient. I'm going to use all the properties of logarithms here, just about all of them. All right, so let's just first of all let's take care of the quotient part. So I can just split this up into the log of a b to the t minus the log, natural log of c equals 20. Okay, so I just use the quotient property there, and now I have a product here, so I can break that up. So I get the log of a plus the natural log of b to the t minus log of c equals 20. Notice I'm writing a new true statement every time. I want to solve for t. I got one more thing I need to do, though I have to get the t out of the exponent position. So I'm going to use the power property to say that the natural log of b to the t is t natural log of b. All right, now we need to do some rearrangement. I am going to start over here. All right, we want to get t by itself, so I'm just going to say, first of all, t natural log of b is equal to 20 minus the natural log of a, if I just subtract natural log of a from both sides, and I can add the natural log of c to both sides. All right, now I can get t by itself just by dividing both sides by the natural log of b. So t is equal to 20 minus the natural log of a plus the natural log of c, all of that is over the natural log of b. Okay? So that's it. I've solved for t in terms of a, b, and c. All right, there's a few common mistakes that I listed here. I want you to take a look at them, just so you don't make these mistakes. All right, so we can't do anything with the log of a sum. All right, you can break it up into the sum of the logs. You cannot do that, because the sum of the logs is the product. Okay, so don't do this. These are all just things I don't want you to do. So they're common mistakes, though. All right, just remember your properties of logarithms, and you won't make a mistake. All right, so take a look at these practice problems, and I will pause the video here. And there's a couple that I want to, I'm not going to necessarily go through the solutions here, but there's a couple that I want to point out to you, or at least the very last one anyway. So I will pause the video. You can do these problems, and then I'll come back with the solutions, and you can check your solutions. All right, so I have written out the solutions now for all of these problems, so you can go through and check to see if you got the same thing I did. Now, if you didn't get the same thing that I did, just send me an email and ask me a question, or ask me in class, or ask me during my office hours, whenever it's convenient for you. So let me, oops, okay, let's scroll down here a little bit. So you can see the answers. All right, let's keep going. All right, so you should be able to check your answers as we go, hopefully. You can pause the video if I'm going too fast through these solutions. And again, like I said, if you have any questions, just ask. All right, there's one problem here that I wanted to make sure you're aware of. And that's this last one. The last one's a little bit tricky. This is a problem where they're trying to make you make a mistake. They're trying to force you to use one of those common mistakes that we talked about briefly. So you have the log of x plus 2 times the log of x squared. Okay, that is not the same thing as the log of x squared times x plus 2. Okay, don't make that mistake. The only way to solve this is to use that zero product property. Okay, so you have two factors. You have a factor log of x plus 2, another factor log of x squared. And if that is equal to 0, then you know one of those two factors is 0. Okay, so that's how you have to solve this problem. There may be a problem in the homework. like this. There may be a problem on the quiz like this. There may be a problem on the test like this. So just be aware of what's happening here. All right. So if the log of x plus 2 is equal to 0, that means 10 to the 0 power is equal to x plus 2. 10 to the 0 power is 1. All right, so here we have the 1. So x plus 2 has to be equal to 1 in order for this to be 0, which means when we solve this, we get x equals minus 1. For the other factor, log of x squared equals 0, that means x squared is equal to 1. All right, and if x squared is equal to 1, then x has to be either positive or negative 1. So our solution is x equals plus or minus 1. Now, of course, we have to check that. If we put plus 1 into the original equation, we don't have a problem. If we put minus 1 into that original equation, we don't have any problem. So both of those solutions check out. So I could put a little check mark here saying, yes, we checked them. All right, so that's all I have for today. We'll see you next time.